Welcome back to the Deep Dive, where we cut through the noise and get right to the core of complex systems.
Great to be here.
Today, we're pulling back the curtain on Maestro Superpod, a name that evokes, well, power and precision, doesn't it?
It certainly does.
Imagine for a moment a system tasked with processing petabytes of data, orchestrating millions of intricate jobs every single day for some of the world's largest companies.
Yeah, it's hard to wrap your head around that scale sometimes.
This isn't a futuristic fantasy. It's the high-stakes reality of Salesforce's Analytics Foundation services. And at the very heart of that immense capability, the conductor of this digital orchestra sits Maestro Superpod.
That's right. Maestro isn't just another piece of software. It truly is the central nervous system for what we call AFS, or Analytics Foundation Services.
AFS, okay.
Yeah, and when we talk about AFS, we're referring to a suite of critical distributed systems. Maestro itself serves as the cluster management and orchestration layer, making sure everything runs smoothly.
But the conductor, like you said.
Pretty much. It works hand in hand with other vital components. M3, our S3-like object store for, petabytes of data.
Petabytes, still staggering.
Then there's Cassandra, which handles our metadata.
Uh-huh.
And Bifrost, our distributed file system that also integrates a crucial shield encryption engine.
Right, Bifrost. We'll definitely get into that.
Oh, yeah. So our deep dive today is all about understanding the profound problem statements this entire distributed system was built to solve.
Okay, the why.
Exactly, the why. And how it evolved into a platform that's not just reliable and available, but also secure and incredibly scalable.
So we're talking evolution, not just a single design.
Absolutely. We're going to explore the initial architectural hurdles, the ingenuity behind scaling for millions of daily ELT jobs.
ELT, extract, load, transform.
Correct. And the groundbreaking solutions that tackled everything from, say, encryption performance bottlenecks to intelligent data placement and robust fault recovery.
Okay, let's unpack this. Our mission today is to truly understand the fundamental challenges Maestro Superpod was designed to overcome.
This isn't just a story about technical fixes, right? It sounds more like a narrative of architectural evolution under extreme pressure.
That's a good way to put it. A team wrestling with monumental problems and finding, well, often ingenious solutions along the way.
So let's journey back. Where did it all begin? What were those very first foundational challenges? It's often hard to picture a massive complex system like Maestro starting small.
True.
Yet even the biggest distributed architectures often have humble, sometimes limiting beginnings.
Absolutely. They evolve.
So what was the initial architectural hurdle Maestro Superpod had to overcome back in those early days? What was the problem statement that really kicked off this entire journey? Yeah, well, the initial problem was a fundamental rigidity in our design. Historically, individual customer organizations, or orgs, as we call them,
Orgs, got it.
they were strictly tied to specific physical hosts. One org, one machine.
One machine for everything.
Pretty much.
Yeah.
Our system used a hashing mechanism to assign all of an org's data to a single machine worker. So if you were org A, all your data, no matter how much, lived on one particular server.
I can see how that might work. Maybe for a while.
Right. It worked for smaller data sets and fewer customers, but it very quickly introduced a hard, immovable limit, a ceiling you just couldn't break through.
I can imagine that rapidly became a bottleneck then. As these organizations grew and their data sets expanded, what were the practical implications? What happened when an org's data footprint started to balloon beyond what a single machine could handle?
You've hit on the core issue. That was precisely the bottleneck.
Right.
As org data and individual data sets grew in size, they inevitably started crossing the storage limits on these individual nodes.
Just running out of space.
Literally. It became impossible to fit a single organization's entire data set onto just one machine. This wasn't just an inconvenience, it was a critical scalability wall.
A hard stop.
Exactly. The system became incredibly inflexible, preventing growth and creating constant operational headaches. This forced a fundamental non-negotiable shift in our architecture.
You had no choice, basically.
Yeah, pretty much. The need for a truly distributed system, one that could spread an org's data across many machines, became undeniable.
So breaking that one-to-one mapping.
This realization set the stage for components like Bifrost, our distributed file system, to come into play,
Yeah.
allowing data to be intelligently spread out.
Yeah.
That was the problem statement. How do we break free from the single host limitation?
That's a classic example of how rapid growth demands a complete architectural rethink, not just an incremental upgrade.
Absolutely. No patching that over.
So, with that architectural paradigm shift forced upon the team, what was the next immense challenge? Because we're talking about processing petabytes of data, which is just
Yeah.
mind-boggling scale.
Yeah. The next massive problem statement was driven by an escalating business requirement, the need to run millions of extract, load, and transform ELT jobs every single day.
Millions. Wow.
Millions. And these jobs weren't just processing existing data, they were constantly generating petabytes of new data.
Generating petabytes daily.
hmm And of course, this ever-growing volume of data needed to be stored, accessed, and processed efficiently.
And you couldn't just keep adding bigger hard drives to those single nodes anymore, could you?
No way.
Trying to manually manage storage for that kind of growth sounds like an impossible task.
Exactly. Trying to store this explosion of data on a fixed set of machines was a non-starter. It inherently lacked the ability to scale up or down as demand fluctuated.
Right. Elasticity was missing.
Totally. You couldn't predict how much data an org would generate tomorrow or how many jobs they'd need to run.
So the problem statement became managing unpredictable, massive scale.
Precisely. This is where Maestro's critical function as the cluster management and orchestration layer truly comes to the forefront. It's responsible for wrangling these vast dynamic data pipelines, ensuring that resources are allocated efficiently and that data flows reliably, no matter the scale.
The traffic cop for petabytes.
You can say that. The fundamental problem was no longer just about fitting data onto a single machine. It was about intelligently managing its entire life cycle across an entire dynamic fleet of machines. Hashtag two friends. Unlocking scalable data transfer and storage. The millions of jobs problem.
So we've established the monumental scale, petabytes of data, millions of jobs.
Yeah.
That implies an enormous amount of data moving around constantly, uploading, downloading.
All the time.
And moving large files reliably, especially at that scale, can be incredibly tricky.
Oh, absolutely.
What was one of the first major pain points that arose when trying to handle these massive data transfers at such an extreme scale? What was the problem statement there?
One of the most critical issues revolved around large file uploads in M3, or distributed object store.
M3, right, the S3-like store.
Exactly. We're talking about crucial large parquet files,
Yeah.
often ranging from 10 to 100 gigabytes.
Huge files.
Yeah, absolutely essential for enterprise analytics. The alarming symptom we saw was these critical files were failing to upload an astonishing 67% of the time.
Wait, 67%? 2 out of 3 failed.
2 out of 3. Think about that.
Yeah.
Large critical analytics files just not making it.
That's not just a problem. That's a full-blown operational and, I imagine, customer confidence emergency.
It was absolutely a crisis. It completely broke entire analytics pipelines for our customers. Jobs failing left and right.
So what was the underlying cause of this catastrophic failure rate? What was the technical problem statement, and how did it impact the various engineering teams involved? Because you mentioned multiple components earlier.
Yeah, the root cause was an architectural relic, really. Our system relied on a single stream upload system.
Single stream, meaning?
Meaning the entire file, all 50 GB or whatever, was sent as one continuous stream. If any part of that massive upload failed, maybe due to a transient network issue, a load balancer resetting the connection.
Which happened?
All the time. Or even a Stark job pausing for a few minutes during its data processing phase.
Okay.
The entire upload had to restart from scratch.
Oh, wow. Back to byte zero.
Back to byte zero. This wasn't just an inconvenience. It was incredibly expensive in terms of both time and computational resources. It led to unpredictable job run times and, extremely frustrating failures.
And you said multiple teams. This sounds like a coordination nightmare.
It was. This problem wasn't contained to a single team. It required coordinating across at least 6 different teams.
6? Okay.
Yeah, each with their own priorities and concerns. For instance, the Spark team was deeply concerned about any API changes that might break existing stable jobs. They wanted stability above all.
Understandable.
The M3 storage team, they wanted to keep the server-side architecture as simple and robust as possible, avoiding unnecessary complexity on their end.
Keep it clean.
Right. And our Maestro team, we were focused on efficient data replication and orchestrating these upload. So you had these different viewpoints.
All valid, but potentially conflicting.
Exactly. This created a critical architectural decision point where we had to navigate these differing priorities and find a solution that satisfied everyone, or at least mostly everyone, while actually solving the underlying problem. The problem statement wasn't just technical, it was organizational.
That's a perfect illustration of how distributed systems engineering isn't just about writing code. It's deeply intertwined with stakeholder management, aligning diverse incentives, navigating those different opinions.
A huge part of it.
So, how did you tackle this reliability crisis for large file uploads, especially with those conflicting viewpoints? What was the solution path?
The vision was clear. We needed a shift to a multi-part upload system.
Like S3 does.
Pretty much, yeah.
Yeah.
Break the large file into smaller, independently uploaded parts. But the path there wasn't straightforward. We immediately ran into a fundamental architectural debate within the teams.
Ah, the debate. What was it about?
Should we go for independent dataset storage, where each part of a file is stored and replicated separately? Or server assembly, where one designated server grabs all the parts and assembles them before committing the final file?
And different teams like different options.
Well, the Maestro team, my team initially, leaned towards server assembly because it seemed simpler. It fit our existing model of one file equals one dataset a bit more neatly.
Right. Seemed less disruptive, maybe?
Yeah, perhaps. It sounds like a trade-off between perceived simplicity and true robustness. What was the critical insight or argument that ultimately guided the decision, especially when different teams had different preferences? How did you navigate that stakeholder disagreement? It was absolutely a trade-off. And this experience deeply reinforced a core principle in distributed systems. Never compromise fault tolerance for perceived simplicity, especially at this scale.
Okay.
We conducted a rigorous technical deep dive, walking through various failure scenarios with all the teams involved. I demonstrated that with server assembly, if that designated leader server crashed during the assembly process, poof, the whole upload is lost. Gone. The application would have no way to recover without restarting the entire thing from scratch. All that work, wasted.
Right. Back to square one.
But with independent dataset storage, each part is stored and replicated with its own fault tolerance. If one part fails or one server holding a part goes down, only that specific part needs to be re-uploaded. The other 99 parts are safe.
Much more resilient.
Exactly. This crucial point, illustrated through concrete failure simulations, actually showing them the potential data loss, helped build consensus across the diverse teams. It showed that true reliability, especially for petabyte scale, lay in distributing the risk, even if it seems slightly more complex upfront.
That's a powerful way to guide a decision, not just stating a preference, but illustrating the real-world consequences of each option. Showing, not just telling.
You have to, especially with experienced engineers.
So independent dataset storage won out. What did the technical implementation of this independent multi-part system look like on the client side?
On the client side, we introduced a significant amount of intelligence. The client could now buffer data either to disk or memory, depending on the situation.
Okay.
And critically, it could throttle the producer, like a Spark job. If its buffers became full, it could tell Spark, hey, slow down, preventing it from overwhelming the network or the storage system.
Smart throttling.
We also implemented sequential upload streams. It's subtle, but important. We avoided reading from disk until a stream failure actually occurred.
Reducing I/O unless necessary.
Exactly, which significantly reduced unnecessary I/O load. We also leveraged parallel upload buffers for concurrent processing of multiple parts.
Making use of parallelism.
Right, and through extensive testing, we determined an optimal part size of 2 GB for uploads. That was a significant jump from the initial 1 GB limits, which boosted performance and reduced the overall number of parts for these truly massive files.
2 gigs per part. Okay.
Yeah, finding that sweet spot took some work.
That's a comprehensive redesign, addressing both reliability and efficiency at multiple layers. What was the ultimate measurable impact of this shift to multi-part uploads? Did it solve the 67% failure problem?
Oh, absolutely. The impact was transformative. We achieved a remarkable 95% reduction in failed uploads for large files, specifically those greater than 2 GB.
95% reduction from 67% failure. Wow.
Yeah. It completely turned around our reliability for these critical analytics pipelines, drastically reducing job failures, improving customer satisfaction. It was huge.
A massive win.
And maybe more importantly, it laid a much better, more scalable long-term foundation for M3, capable of handling the ever-increasing demands of petabyte-scale data. It set us up for future growth.
Incredible. So uploads were tackled, transforming a reliability crisis into a robust solution. But in a system dealing with petabytes, the data eventually needs to come out, right?
Always does.
Did you find that downloading large files presented its own set of unique, equally stubborn challenges? Was there another problem statement lurking there?
There absolutely were, yes. The existing AFS S3 download implementation, which utilized the older V1 transfer manager.
J1 Transfer Manager, okay.
It also had serious issues, particularly when dealing with a mixture of many small files and very large files, often 10 GB or more. This became another critical problem statement for us.
A mix of file sizes causing trouble. What kind of specific problems were cropping up with these downloads? It sounds like resource starvation might have been a factor, maybe.
Exactly. Resource starvation was a huge part of it. The system suffered from several bottlenecks. Downloads would fail multiple times.
Retries burning resources.
Right. And often they would exhaust the entire download thread pool, which could be up to 1,000 threads with a single large file.
One file takes all 1,000 threads.
Potentially, yes. It would just hog them all, causing severe thread starvation across the system. This led to a cascade of HTTP errors, messages like unable to execute HTTP request, the target server failed to respond.
Because no threads were available.
Correct. It meant our applications couldn't get the data they needed in a timely or reliable fashion. And other, smaller downloads would also get stuck waiting behind the big one.
That sounds like a fundamental design flaw if one large file can monopolize all resources like that. What was the core technical difference that contributed to these issues, especially comparing it to newer, more efficient approaches?
Well, one key inefficiency was the V1 Transfer Manager's polling mechanism.
Polling?
Yeah, it's continuously checked for download status.
Oh, were you done yet?
Are you done yet?
Yeah.
This consumed more CPU cycles and API calls. Or, if we tried to reduce the polling frequency to save resources, it introduced longer delays in detecting completion or failures.
Neither sounds great.
No, it was less than ideal, especially compared to the more mature asynchronous processing capabilities offered by newer versions of the AWS SDK, like the V2 API.
Ah, V2. What did that offer?
V2 introduced non-blocking I/O using things like completable future. This made it far more efficient and scalable for high concurrency applications like ours. It also offered modular dependency management, meaning we only needed to include the services we actively used.
Smaller footprint.
Exactly. Resulting in smaller application binaries and a more streamlined configuration, just better designed for modern high-throughput systems.
So it sounds like the solution was to move to a more modern and efficient API, like V2. But what did that entail for Maestro? Was it a straightforward swap, or did you need to custom build quite a bit?
Oh, it was far from a straightforward swap. The strategic decision was to migrate to the AWS Common Runtime, or CRT, S3v2 API.
CRT, okay.
This API is specifically designed for high-performance applications. However, to gain the necessary granular control over multi-part downloads, especially to implement the specific dataset concurrency limits we needed to prevent that resource starvation.
Right, the throttling you mentioned.
Exactly. To get that control, Maestro had to ditch the V1 Transfer Manager entirely.
Ditch it. So rewrite that logic.
Pretty much. This meant we essentially had to re-implement a lot of the nice high-level functionality Transfer Manager provided, like the simplified file management, custom automatic resilience, retry logic.
What convenience features?
Right. We basically built a more optimized custom version of it ourselves, tailored specifically for our extreme scale requirements. That was a significant piece of work.
That sounds like a major undertaking, essentially rewriting core download logic. What were the key requirements for this new custom-built system then? What did it have to do?
Okay, number one, the new system absolutely had to be efficient and scalable for transfers between S3 and our pods. No question.
Performance parity, at least.
Or better. It needed to handle large volumes of data and high concurrency reliably without degrading performance compared to our existing EBS volume solutions. And crucially, it needed sophisticated throttling capabilities.
Back to throttling.
Yes. We needed to limit total concurrency across the entire system, no more than 1,000 concurrent downloads overall. But critically, we also needed to prevent a single large dataset from monopolizing resources by limiting dataset concurrency to no more than 50 concurrent downloads for any particular dataset.
Ah, per dataset limits. That's key.
That specific throttling mechanism was key to preventing the starvation issues we'd seen before with V1.
And what made the AWS CRT API, despite requiring all this custom implementation work, the right choice for this complex set of requirements? Why go through that effort?
The AWS CRT API offered significant advantages that justified the effort. It's designed from the ground up for optimized performance, lower memory and CPU consumption, which is huge for large file transfers at our scale.
Resource efficiency.
Massively important. It provides efficient non-blocking I/O, essential for high concurrency scenarios, and advanced features for fine-grained control over operations, exactly what we needed for that custom throttling. Now, it did require external native dependencies, which added a bit of complexity to the deployment setup. Not pure Java anymore.
Trade-offs.
Always trade-offs. But the raw performance and resource utilization benefits were undeniable. For us, operating at this scale, it was the clear winner in terms of performance and resource efficiency, which are paramount for AFS.
That granular control and performance boost really highlights the need for a deep understanding of the underlying infrastructure, not just using off-the-shelf components sometimes.
Sometimes you have to dive deep.
One more thing on downloads. What about the size of the individual parts in a multi-part download? And you mentioned optimizing that for uploads. Was that another factor that needed optimization for downloads too?
Yes, absolutely. That was another significant factor that often gets overlooked. The V1 Transfer Manager had hard-coded part sizes 5 MB for uploads and 8 MB for downloads.
Fixed sizes.
Fixed and relatively small. This might seem minor, but it effectively imposed a 50,000 millib or 50 GB file limit, because AWS has a maximum of 10,000 parts for any single multi-part object.
Ah, the 10,000 part limit.
Right. If you had a 100 GB file, for example, with 5 MB parts, you'd need 20,000 parts. Boom, impossible to upload or download using that mechanism.
So the hard-coded size limited the max file size?
Correct. Our new V2 design allowed for optimal dynamic part sizes. For uploads, we found 64 MB or more worked well. For downloads, maybe 8, 16 MB, or even 32 64 MB in high bandwidth environments.
Flexibility.
Exactly. This flexibility and the understanding that upload and download part sizes don't necessarily need to match was crucial for handling truly massive files efficiently and reliably without hitting those arbitrary limits. Hashtag 3. The data encryption conundrum. Security versus performance.
Okay, so we've tackled the movement of data, both uploading and downloading, at petabyte scale. Huge improvements there.
Yeah, big steps forward.
But with enterprise-level analytics, data security is absolutely non-negotiable. You mentioned Bifrost and encryption earlier. What was the mandate around encryption and how did it initially integrate into the system, especially considering the performance implications we know encryption can have?
Right. Security first, always. For Salesforce AFS, managing encrypted dataset processing for our enterprise customers was a core and immutable mandate. Non-negotiable.
Got it.
We had to adhere to extremely strict security requirements, including things like FIPS-level encryption standards. The existing solution relied on Bifrost, which leveraged the open-source ENCFS file system running on SUS file system in user space.
FUSE, okay, user space file system.
Exactly. This setup provided transparent encryption and decryption capabilities, which was crucial for various analytics workloads, as it meant applications didn't have to explicitly handle crypto operations themselves. It just happened magically from their perspective.
Transparent encryption sounds ideal from an application perspective, right? Just read and write, and it's encrypted underneath.
That's the goal.
But I imagine getting it to work under the hood must have presented some unique architectural and performance challenges, especially when integrating with existing processes like, say, query jobs. How did that work?
It absolutely did present challenges. The necessity for transparent encryption came from how our query jobs operated. They often use memory mapping.
Memory mapping, map.
Yeah, map, for sequential file access.
Yeah.
It's very efficient for reading large files as if they were just arrays in memory.
Super fast access.
Right. However, standard memory mapping completely lacked native encryption and decryption hooks. There was no direct way to integrate crypto operations at that low level within the kernel's map function.
No place to plug in the crypto.
Exactly. This meant we absolutely had to go under the hood, below the kernel, and leverage Fuse to perform that transparent encryption and decryption. Fuse effectively intercepts file system calls, reads, writes, performs the crypto in user space, and then passes the result back, making the encrypted data accessible to applications without them needing to explicitly handle the crypto.
Okay, so FUS was the necessary bridge to make transparent encryption work with things like map.
It was the necessary piece, yes.
But what kind of performance impact did this low-level user space interaction introduce? It sounds like there could be a lot of overhead switching between kernel and user space constantly.
You've hit the nail on the head. That was the next major problem statement. Despite its necessity for transparent encryption, the USC architecture introduced significant performance bottlenecks.
How bad was it?
Pretty bad. Each read or write operation required 4 or more context switches between the kernel and user space,
4 switches per operation.
at least. And a context switch is essentially the CPU pausing one task, like our application's data read, saving its state, switching its focus to another task, like handling the FUSE process in user space, processing that, saving its state, and then switching back to our application.
That sounds expensive. Lots of overhead.
It seriously hogs CPU cycles, just switching back and forth.
Mm.
USE also operated on fixed 4KB blocks, which was highly inefficient for the larger sequential reads common in our analytics workloads. We read megabytes sequentially, not 4KB chunks.
Not optimized for analytics patterns.
Not at all. Furthermore, our specific workflows within FUSE were effectively single-threaded, preventing true parallelism for crypto operations. And data was copied multiple times through different user space buffers,
More memory copies.
creating memory bandwidth bottlenecks and increasing garbage collection pressure in the JVM. It was a cascade of inefficiencies.
Wow, that's a lot of hidden costs just to achieve transparent encryption. Can you give us some numbers on the quantified impact of this USE overhead? Throughput, CPU.
Absolutely. Throughput was severely limited. We were maxing out at only 1.1 to 2 gigabit per second, which sounds like a lot, but was well below our hardware capabilities, especially with fast SSDs.
Okay, and the CPU.
Even more telling, 25 to 30% of the total CPU time was spent just on context switching. Not on useful work like processing data or even doing the encryption itself, but just managing the switches between kernel and user space.
A quarter of the CPU wasted on overhead.
Yeah. This was clearly an unsustainable situation for a petabyte scale system and represented a significant drag on our overall analytics performance. The problem statement was clear. QD gives us transparency, but kills performance.
So, a clear problem. QC was essential for security mandates, but a major performance bottleneck. How did the team initially try to solve this? What was the first attempt? And what happened when they tried to remove FUSE from the picture?
Right, so the initial and seemingly logical approach was, okay, FUSE is the problem, let's eliminate it.
Whip it out.
Yeah, the idea was to create a direct native Java implementation of the ENCFS logic. We thought, cut out the middleman, cut out the context switching, it'll be faster. A single-threaded native solution.
Makes sense on paper.
It did. However, this initial attempt resulted in a devastating performance regression.
Worse, not better.
Much worse. Instead of speeding things up, our end-to-end pipeline became 12.5% slower, took 105 minutes compared to the original 93 with FUSE,
Wow.
and the decryption throughput itself, the part we tried to optimize, was 30 to 60% slower than with FUSE.
That's unexpected. And painful, I bet.
It was a very hard lesson,
Yeah.
especially because this happened just weeks before a critical launch with major customer commitments tied to it. Huge pressure.
Ouch. That's a humbling and very hard lesson to learn, especially under pressure like that. What was the aha moment? What helped identify what went wrong, and what deeper principle did you learn from that initial misstep?
It was indeed humbling, but it led to a crucial insight. After a lot of head-scratching and deep profiling, the critical realization was that FUSE, despite all its overhead and context switching,
Yeah.
was implicitly providing valuable parallel processing capabilities.
Hidden parallelism.
Exactly. Our single-threaded native replacement, in its zeal to remove FUSE's costs, and unknowingly eliminated this hidden benefit.
Mm.
We were so focused on removing the cost of context switching that we completely missed the value FUSE was providing by handling multiple concurrent file operations from the OS, even if inefficiently.
So you threw the baby out with the bathwater, essentially.
Pretty much. This forced us to engage in a systematic root cause analysis, moving beyond our initial assumptions. The key insight was, you can't just assume a component is bad or inefficient based on one metric like context switching. You have to deeply understand why it's working for you, even if its visible overhead seems high, before attempting to replace it. We needed to replicate FUSE's parallelism explicitly, not just remove FUSE.
So the solution wasn't just about removing FUSE, but about understanding and explicitly replicating its hidden strengths. Fascinating. What did the redesigned multi-threaded architecture look like to achieve this?
Exactly. The redesign focused squarely on explicitly replicating that parallelism we'd lost. We implemented a multi-threaded worker pool architecture.
A worker pool. Okay.
This involved a configurable worker count, which we optimized based on available CPU cores on the host, a job queue for efficient work distribution among those workers, and crucially, we introduced a shared buffer pool for memory management.
Buffer pool. Why was that important?
To minimize that memory copy proliferation and garbage collection pressure we saw earlier, we optimized for 64 KB buffers. which seemed to be a sweet spot. And a key lesson learned from the initial failure was that every step of this new design was rigorously measured and profiled.
No more assumptions.
No more assumptions. We needed to prevent any further regressions and ensure we truly understood the performance impact at each stage. Data-driven design.
That's a fantastic example of learning from failure, iterating, and coming back stronger with a much more data-driven approach. What was the final triumphant result of this multi-threaded approach to decryption?
Well, triumphant feels good after that initial stumble. This multi-threaded architecture achieved a staggering 60% improvement in overall decryption performance compared to the original FUSE Bifrost system.
60% faster than FUSE.
60% faster.
Right.
And maybe more broadly, it brought architectural consistency across the board. We ended up with a unified and consistent throughput of approximately 300 millibeats per second for M3 client GT operations, regardless of whether the data was encrypted or not.
Consistent performance, encrypted or not. That's huge.
It was a huge step forward for both security and performance, demonstrating that with careful, measured design, you absolutely can achieve both. You don't always have to trade one for the other.
That's a great example of solving a complex problem at scale, transforming a security necessity into a performance win. But what happens when the keys themselves become a source of complexity? We're talking about enterprise customers, so key management must be incredibly dynamic, right? Key rotations and things.
Oh, absolutely. Key management is a whole other beast. And yes, it led to another critical problem statement, this one threatening data integrity itself.
Data integrity. Okay, that sounds serious.
It was. A data corruption problem emerged where an encrypted data set could become corrupted under very specific but increasingly common conditions.
What conditions?
Okay, it would happen if, 1, the data set was encrypted, 2, it existed on 2 different hosts, but encrypted with different encryption keys.
Different keys for the same data? How does that happen?
Often due to legitimate customer key rotations. A customer might update their encryption key for compliance or security reasons, or sometimes due to a new internal data fetch flow, causing data to be re-encrypted with a different key version. So now you have copies of the same logical data set under different keys on different machines.
Okay, I see the setup. What triggers the corruption?
The problem then manifested when our dataset downloader, the thing fetching the data, attempted to download that dataset from multiple hosts simultaneously, using the parallel download capability we built.
Ah, using the faster parallel downloads.
Right. But some of those hosts had the data encrypted with the old key, and some had it with a new key.
And what was the outcome of that scenario? I imagine decrypting with the wrong key isn't just not ideal.
It leads to complete data chaos.
Precisely.
Files downloaded from hosts with the wrong key would be decrypted incorrectly and essentially become junk, garbled bytes.
Just useless data. And you said this became more frequent.
Yes. This wasn't a rare, one-off theoretical edge case. The problem was exacerbated by a few factors converging. Customers were rotating their keys more frequently. Our internal FLUX disk encryption upgrades, that's our system for managing disk-level encryption across the fleet, could sometimes cause datasets to become temporarily orphaned with different keys. And critically, the general availability of parallel downloads in version 236 significantly increased the probability of downloading from multiple hosts with different keys simultaneously.
So the performance improvement actually made the corruption risk higher.
Ironically, yes. It surfaced the underlying key inconsistency problem much more often, making the corruption issue much more common and urgent to fix.
That's a serious threat to data integrity, a foundational principle of any data platform. What was the immediate response to stop the bleeding? You can't have data corruption. And then what did the long-term solutions for intelligent encryption handling and key management look like?
Yeah, stop the bleeding was priority 1. Given the critical nature of data corruption, an immediate short-term fix was imperative. We essentially rolled back a feature. We temporarily disabled parallel downloads specifically for encrypted datasets.
Sacrificing speed for safety.
Exactly. We forced downloads for encrypted data to come from only a single host. We acknowledged that this sacrificed some availability and redundancy, maybe slowed things down a bit, but it was absolutely critical to stop the corruption immediately and prioritize data integrity above all else.
Okay, immediate fix done. What about the long term?
For the long term, particularly for copy TODI requests, that's typically when ELT jobs import datasets into the system.
Right.
The ideal solution was to decrypt bytes with the correct key during the file download stream before they were even written to disk locally.
Decrypt on the fly during download.
Yes. We extended our Maestro HTTP server to pass the secreted and version it basically, identifiers for the correct encryption key in the HTTP headers of the download request. This allowed the file downloader component on the receiving end to transparently decrypt using the correct key as the bytes arrived.
Smart. And that helps performance too, right?
A huge I/O boost. It eliminated the incredibly inefficient cycle of download encrypted bytes, write encrypted bytes to disk, read encrypted bytes back from disk, decrypt them in memory, write decrypted bytes back to disk, just decrypt straight from the network stream to the final disk location. Much cleaner.
That makes a lot of sense. Decrypting on the fly saves a lot of unnecessary disk I/O.
What about pure copy out operations? Like when Maestro replicates datasets to other hosts within the cluster for redundancy or locality? Were there different strategies considered there, given they often happen outside a direct job context? Yeah, peer copy imposed unique challenges because it often happens outside a direct job context, meaning the specific authentication credentials or encryption context for a user's job might not be readily available when Maestro decides to replicate data between its own nodes.
Right, system-level operation.
Exactly. We considered several options there. One was to try and be clever, conditionally allow multi-host downloads, dynamically check if all source hosts had the same encryption keys for the dataset. If yes, great, allow parallel downloads. If no, revert to a single source.
More complex logic.
Definitely more complex. A simpler approach was just single source. Always transfer the dataset encrypted from a single authoritative source, skipping the whole decrypt-encrypt cycle during peer copy. Simpler, less performant maybe, but safe.
Okay.
The most complex, but potentially most robust architecturally, was to re-encrypt to a consistent secret. This involved downloading metadata, decrypting with the source key, and then re-encrypting everything with the destination host's preferred or standard key.
Standardizing the key during replication.
Right. This could potentially leverage our existing GDOT, or Global Distributed Token Service, that's our internal system for secure service-to-service authentication, to acquire the necessary secrets outside of a job context. But this required pretty extensive API changes across multiple systems.
So multiple paths, each with different trade-offs in complexity, performance, and security.
Exactly. It's rarely one perfect answer in these distributed systems. It's about choosing the best set of trade-offs for your specific needs and constraints.
That's a complex landscape of security challenges and architectural decisions, moving from encryption keys and data integrity to the very bedrock of communication, the network layer itself. What was the next big performance hurdle that cropped up, particularly with client-side interactions in M3? You mentioned performance issues earlier.
Yes. This is another puzzling one. Despite all the server-side optimizations we put in place in M3 and the decryption improvements we just talked about,
Yeah.
we observed a really strange anomaly. M3 GET performance in production remained severely limited. We were stuck at around 25 to 35 millibits per second.
Still, after all those improvements.
Still, which was far, far below the 300 millibar per second we consistently demonstrated in controlled testing environments after the decryption fix.
Okay, that's a huge disparity between test and production, nearly 10x slower in the real world.
Exactly. The question again was, where on earth was all that performance going? This was another critical problem statement with significant business impact because slow data access slows down everything else.
How did you pinpoint the exact bottleneck this time, when everything on the server side seemed optimized and the data was already decrypted efficiently?
This is where systematic deep dive profiling became absolutely critical. Again, we couldn't just guess. We used tools like YourKit to profile the M3 client process during production GET operations.
Profiling the client, not the server.
Right, profiling the application making the request. The results were quite shocking and revealed the hidden culprit. A staggering 85% of the CPU time on the client side was consumed by bouncy castle FIPS cryptographic operations.
Crypto again, but the data was already decrypted.
Not data decryption crypto. This was crypto during the TLS-SSL negotiation and transfer, securing the connection itself.
Ah, the secure channel setup and teardown, TLS.
Exactly. It wasn't network I/O, it wasn't disk I/O, it wasn't our application code parsing the data. It was the crypto library used for the secure communication channel itself. Bouncy castle in FIPS mode, eating almost all the CPU.
85% of the client CPU just on TLS SSL crypto. That's incredible. Essentially, a colossal hidden tax on every secure connection.
It was a huge hidden tax.
What specifically about Bouncy Castle FIPS was causing such a massive bottleneck? Why was it so slow?
It turned out to be a combination of factors related to its implementation, particularly when running in that strict FIPS compliant mode. First, Bouncy Castle FIPS used extremely small 16-byte internal buffers for AES operations.
Tiny buffers.
Very inefficient compared to optimal hardware level sizes. Second, And crucially, it had no support for AES-NI hardware acceleration.
AES-NI, the instructions built into modern CPUs.
Yes, exactly. Modern Intel and AMD CPUs have dedicated instructions to dramatically speed up AES encryption and decryption. Bouncy Castle FIPS wasn't using them.
So it was doing it all in software.
Pure Java software implementation, which our benchmark showed was about 97.5% slower than what could be achieved with the hardware-accelerated alternatives available in other Java crypto providers like the default SUN-JCE.
97% slower. Wow.
Yeah, essentially our system was doing all its heavy crypto lifting in software, burning CPU cycles like crazy, when the hardware sitting right there was perfectly capable of doing it much, much faster, simply because the chosen library, in FIPS mode, wasn't leveraging those capabilities.
So the solution clearly involved leveraging that hardware capability. What did the TLS-SS optimization for the M3 client look like to unlock that hidden performance? How did you switch to using AES-NI?
The solution involved a targeted configuration approach. We didn't need fixed compliance for all internal TLS communication, only for specific regulated workflows. So first, we explicitly disabled FIPS mode for these non-regulated internal TLS operations where possible.
Turning off FIPS where it wasn't strictly needed.
Right. Then we configured preferred TLS providers in the Java security settings, prioritizing ones like SUN-JCE, which does support hardware-accelerated AES-NI.
Telling Java to use the faster provider.
Exactly. And we also carefully optimized the allowed cipher suites, favoring those known to perform well with AES-NI. This allowed the system to automatically use the faster hardware-accelerated cryptography where appropriate, bypassing the slow, software-only Bouncy Castle FIPS implementation for those specific use cases.
And what was the impact of these targeted configuration changes? Did it really unblock that huge performance deficit you were seeing in production? Did you get closer to the test environment speeds?
It was a dramatic transformation. Instantly, M3 GET throughput skyrocketed from that struggling 25-35 millibit per second to a healthy 110 millibits per second.
Wow, a 3-4x improvement just from TLS tuning?
Easily, and more than 214% improvement overall.
TLS handshake time, the setup part was slashed by 68-70%.
Much faster connections. And CPU utilization for cryptographic operations on the client plummeted from that insane 85% down to a much more reasonable 25%.
Huge CPU savings.
The key insight here, or maybe the confirmation, was that network I/O, as expected, finally became the primary time consumer again. We had successfully eliminated the crypto bottleneck and truly moved the performance bottleneck back to the network, where it arguably should be for a data transfer operation.
That's a fantastic outcome, not just technically, but organizationally. For our listeners building their own complex systems, what's the broader lesson here about profiling and never assuming where a bottleneck lies? Even in seemingly robust, standard third-party libraries like Bouncy Castle?
That's a critical point, I think. The systematic debugging approach, where we didn't just guess but rigorously profiled, actually evolved into a reusable performance investigation framework that was adopted across multiple platform teams at Salesforce.
A reusable framework.
Nice. Yeah. The lesson is really twofold. First, never, ever assume where your performance bottleneck is. Always measure. Profile, profile, profile. Second, even highly regarded, widely used third-party libraries, especially when configured for specific compliance modes like FIPS, might introduce unforeseen overhead that can only be uncovered through deep profiling in your specific environment and workload.
Don't trust, verify.
Pretty much. This framework, born from this TLS investigation, led to significant performance improvements in other areas too, like Spark Java execution, ETL pipelines, data replication across the organization. It just proved the power of having a structured, data-driven approach to solving complex, often hidden performance problems. #4, smartening up data placement and orchestration beyond simple slots.
Okay, moving from raw performance and security to overall system efficiency. Getting the most out of your infrastructure is always key, right? Especially at this scale.
Absolutely. Waste is expensive at petabyte scale.
What was the initial challenge when it came to how datasets were placed across all those machines in Maestro? Why wasn't the initial placement strategy as efficient as it could be? What was the problem there?
Initially, dataset placement relied on a very, very simplistic model. It basically just checked the number of available slots on each machine. Like, can this machine theoretically run another job or hold another dataset? Yes, no.
Just a simple count.
A simple count. This basic check completely overlooked other crucial factors about the host's current state, like what's its actual CPU load right now? How much disk space does it really have free?
Ignoring the actual utilization.
Totally. This was a significant problem statement because in a petabyte scale environment, Inefficient placement quickly leads to resource bottlenecks and wasted capacity.
And what were the direct consequences of this simplistic slot counting approach? I imagine it quickly led to some glaring inefficiencies, like some machines getting hammered while others sat idle.
It definitely did. Exactly that. It led to very uneven traffic distribution and resource usage. The Kubernetes scheduler, for example, which also used slot counts, would tend to prefer certain nodes over others because they appear to have more slots, even if they were already busy with CPU-intensive tasks or had significantly less actual free disk space than other nodes.
Leading to hotspots.
Right. This resulted in what we called flooded hosts. Machines that were overloaded, struggling, dropping requests, while other perfectly capable machines sat largely underutilized. This created overall suboptimal resource utilization across the cluster, wasting valuable compute and storage capacity and impacting stability.
Okay, so a simple slot count clearly wasn't cutting it for intelligent orchestration at scale. How did the team introduce more intelligence into dataset placement? How did you make it smarter to distribute the load more effectively and avoid these flooded hosts?
The team introduced CPU-aware and disk-space-aware dataset placements. This was a significant upgrade from the basic slot model.
Looking at actual load now.
Exactly. It involved using a more sophisticated weights algorithm to score potential hosts for placing a new dataset. This algorithm would factor in not just available slots, but also the current CPU load and, crucially, the actual free disk space available on the node.
Giving a more holistic score.
Right, giving a much more holistic view of a host's readiness to take on new data. The goal was to ensure that a host wasn't just theoretically available, but actually optimal for the new dataset based on its current state.
And did this new, more intelligent weight-based approach actually make a measurable difference in how balanced the system became across your vast infrastructure? Could you see the improvement?
Oh yeah, we measured it closely. It made a demonstrable improvement. After the new algorithm was applied and rolled out, we observed significant reductions in the average deviation of free disk space across various production environments and availability zones.
Average deviation, so less variance between nodes.
Exactly. Less variance means more balance. For instance, in our product low latency workers one specific environment, the average deviation dropped impressively from approximately 0.08 down to about 0.01.
That's a huge reduction in spread.
It really is. It indicates a much more even distribution of data and significantly better utilization of disk resources across the entire fleet, which means fewer flooded hosts, a more stable environment overall, and better use of our hardware investment.
That's a significant improvement in balance. Was this weights algorithm a one-and-done solution, though? Or was there continuous refinement needed as the system continued to scale and evolve? Did new challenges emerge?
It's never one and done at this scale. There was definitely a need for continuous refinement. We acknowledged pretty quickly that the initial percent-based algorithms for calculating that balanced weight weren't quite aggressive enough in some situations.
Not aggressive enough.
Yeah. For example, if you have one availability zone with only, say, 2 really full nodes and another AZ with 20 mostly empty nodes, a simple percentage-based calculation might still be hesitant to move data aggressively to the emptier AZ.
Right. The averages could still look okay, even with big imbalances.
Exactly. We realized we needed further tuning to better reflect the actual deviation from average disk usage, taking into account imbalances in both free disk space and the number of nodes across different availability zones. The goal was to make the algorithm more aggressive in balancing the load, proactively shifting data to prevent even minor imbalances from growing into major problems over time.
Constantly tuning the balance.
Furthermore, for our long-running jobs and the associated auto-scaling, we actually proposed building our own custom scheduler.
Your own scheduler instead of Kubernetes.
Yeah. Because the standard Kubernetes scheduler, while good, has its limitations, especially around understanding our specific application's job queue depth or other custom metrics.
Yeah.
Our own scheduler would explicitly take job count, expected resource usage, and other dynamic metrics into account to give us even finer-grained control over resource allocation and dynamic scaling for those demanding LRJs.
Wow, taking full control. So intelligent placement is key, and it's a continuously evolving challenge. But what happens to data that's no longer needed? With petabytes flowing through, I imagine old files and data sets can pile up incredibly fast if you're not careful.
Oh, absolutely. Data cleanup is a huge operational challenge.
What was the cleanup conundrum Maestro faced? What was the problem statement around getting rid of old data, and what were the consequences of inefficient data retention?
This became a growing and really critical problem as the system scaled and held more and more data. Maestro's dataset finder component was responsible for scanning the data directories on each worker machine.
Scanning the actual disks.
Yeah, scanning the disks to update an in-memory cache of dataset last access times. This cache was then used for our least recently used LRU deletion policies, basically, figuring out which old unused datasets could be safely removed to free up space.
You know, the LRU cache idea.
Right. The system initially assumed, based on earlier scales, a maximum of maybe 100,000 files or datasets to visit per worker during a full scan, which we calculated would allow for a full scan within about 12 hours.
Okay, 12 hours sounds potentially manageable for a full LRU scan across the fleet. But this is production reality we're talking about. So I'm guessing that 100,000 file assumption didn't hold up as data volumes exploded.
Not even close, unfortunately, no. Production analysis revealed a massive buildup far, far beyond our initial estimates. The total walk count, the number of files the scanner actually had to look at, could go as high as 2.4 million files per worker in some superpods.
2.4 million instead of 100K.
Yeah, a huge difference. This stretched the full scan times from the expected 12 hours to multiple days. For example, we saw up to 79 hours over 3 days for a single scan in the IF4 SP3 superpod.
3 days to figure out what's old.
Exactly. This drastically reduced the precision and effectiveness of our LRU dataset deletions. Data that hadn't been accessed in months might stick around for days longer than it should have, simply because the scan hadn't finished yet to mark it for deletion. Disk space was being wasted, performance could degrade as workers struggled to manage this enormous index of files, and our cleanup wasn't timely.
So not only were legitimate old data sets piling up because the scan was too slow, but were there other forms of lingering debris contributing to disk space issues? Maybe temporary files that should have disappeared automatically?
Yes, absolutely. That was another part of the problem. We found that critical temporary directories, like .trash, where files go before final deletion, download for incomplete downloads, and .re-encrypt, used during key rotations.
Temporary work directories.
Right. These were not being consistently deleted, especially in certain environments like our internal Falcon testing environment, but also sometimes in production. These are directories meant for transient data during various operations, and they should be cleaned up promptly.
But they weren't always.
No. This further contributed to disk space utilization issues, creating more pressure on an already strained system. It wasn't just old, unused data sets. It was also this temporary file clutter that should have disappeared after its purpose was served, creating unnecessary noise and consuming valuable disk space. Our investigations also found a specific issue where M3 datasets were sometimes deleting their version directories but leaving behind the empty parent container directories in certain batch worker scenarios, which also contributed to that massive file count buildup.
Empty directories counting towards the millions. Okay, so how did the team go about optimizing dataset inventory management? How did you tackle this multifaceted accumulation problem and improve cleanup reliability?
Well, beyond fixing the specific M3 container issue, we needed a more systemic approach. One major idea the team brainstormed was rethinking how we tracked last access time altogether, instead of the periodic full disk scan feeding an in-memory cache on each worker.
The slow scan method.
Right. The idea was to potentially move last access date management to a centralized database. Workers could then update this database much more frequently, maybe even on each access.
A central real-time tracker.
Exactly. This would offer much more precise, up-to-the-minute access dates for our LRU policies, enabling far more efficient and accurate cleanup. It was a significant architectural change, moving from a distributed in-memory model to a centralized persistent one with its own trade-offs, but it offered a path to much better precision.
A big shift. And what about the temporary files?
And finally, yes, implementing more robust mechanisms, better monitoring, and stricter cleanup routines to ensure the consistent, timely cleanup of those temporary and detritus directories like .trash, .download, .re-encrypt was crucial. Just better hygiene to effectively manage disk space moving forward and prevent future accumulation of that kind of clutter. #tag5. Robust fault tolerance and recovery when things go wrong.
Okay, so we've covered scaling, performance, security, efficiency, cleanup. But even with all the clever optimizations, smart data placements, and security enhancements we've discussed, things inevitably go wrong in large distributed systems. Right?
Always. Failure is the normal state, not the exception at scale.
So fault tolerance and recovery are absolutely paramount. What was the initial state of fault tolerance and recovery in Maestro? Was it robust from day one, or did that become another critical problem statement as the system scaled?
Yeah, robust from day one would be optimistic.
Hmm.
Initially, the system simply lashed comprehensive fault and recovery mechanisms. It was built for a different, simpler era of scale and complexity.
Less focus on failure modes early on.
Perhaps less need for complex recovery when failures were rarer and impacted fewer customers. But as the scale and complexity of our operations grew exponentially, this lack of robust recovery became an increasingly critical vulnerability.
A major risk.
Huge. Without robust recovery, even minor incidents, a single machine failing, a transient network glitch, could cascade into significant outages, data inconsistencies, or prolonged downtime, directly impacting our enterprise customers who rely on this platform. We needed better ways to handle failures gracefully.
And as systems evolve and move to new environments, like you mentioned moving to Kubernetes earlier, that can introduce entirely new sets of failure modes and problems, right?
Oh, absolutely. New environment, new problems.
What happened when the platform began migrating to Kubernetes, specifically for those long-running jobs we talked about, the ones that needed to persist state for hours sometimes?
This was a particularly challenging and frankly high-stakes transition. In our traditional bare metal environment, the way we deployed, Maestro processes could often survive releases. We could update the Maestro software without necessarily killing the jobs it was managing.
Jobs kept running through updates.
Often, yes. Which allowed those long-running ELT jobs to continue uninterrupted even as we deployed updates to the core system. However, during the migration to Kubernetes, we discovered a critical flaw, kind of late in the game.
What was it?
Typical Kubernetes pod restarts during deployments. Standard practice for rolling out updates in K8s were killing these long-running jobs.
Just terminating them mid-run.
Yep. Jobs that often took hours to process multi-gigabyte datasets were just getting wiped out because their managing Maestro pod got rescheduled or updated. This critical flaw was discovered just weeks before a major production release with important customer commitments tied to it.
Weeks before launch! Oh no!
Yeah, it created immense pressure on the team, a real uh-oh moment.
That's a classic high-stakes, last-minute discovery that forces rapid, innovative thinking. How did the team respond to this? How did you solve the problem of Kubernetes' ephemeral container environment killing critical, long-running, stateful jobs?
We had to be incredibly agile and innovative. There wasn't an off-the-shelf solution. A key innovation was to implement what we called the job isolation pattern.
Job isolation pattern, okay.
This meant fundamentally decoupling the execution of long-running jobs from the main Maestro orchestrator lifecycle. We simply couldn't have critical, hours-long jobs dying simply because a core Maestro orchestrator pod was restarting for an update or maintenance. That was the new problem statement Kubernetes introduced. How do you run long jobs reliably in an ephemeral world? And we needed a Kubernetes native solution.
So what was the concrete solution that enabled this job isolation? How did it ensure jobs could run independently and recover gracefully, even when their underlying infrastructure was transient?
The solution was the introduction of Maestro-lite.
Maestro-lite, a lighter Maestro.
It's exactly a lighter, specialized version of Maestro, specifically designed only for long-running jobs, or LRJs. It's spun up by Buzzard, that's our higher-level job scheduler, in its own dedicated Kubernetes node pool, separate from the main Maestro fleet.
Dedicated pool for LRJs.
Right. It runs a single LRJ, does nothing else. And then, crucially, it gracefully shuts itself down once that single job is complete, freeing up its resources.
One job, one Maestro-lite pod.
Pretty much. The crucial part for persistence and recovery was how the jobs themselves behaved within Maestro-lite. These jobs were designed to commit their final datasets to reliable object storage, like M3 or S3, upon successful completion.
Saving state externally.
Yes. And furthermore, a peer copy of the dataset to another Maestro node was initiated before the Maestro-lite pod terminated, ensuring that the job state and its output persisted beyond the ephemeral lifecycle of that single pod. If the Maestro pod died unexpectedly mid-job, we'd lose the work for that job, but we had mechanisms to restart it. If it died after completion but before peer copy finish, the data was safe in M3 S3.
So multiple layers of ensuring the output survives pod death.
Exactly. Decoupling the job's lifecycle and output from the pod's lifecycle.
That's a brilliant way to handle the ephemeral nature of containers while maintaining long-running state and ensuring data persistence. What was the tangible impact of this Maestro-lite and job isolation approach on reliability and efficiency for those LRJs?
This approach dramatically improved reliability for LRJs and had significant downstream benefits. For instance, one of our major customers, Telstra, saw impressive time savings. We measured a maximum runtime job saving of 6.5 hours for one of their longest jobs and a pre-95 runtime saving of 6.2 hours across their LRJs.
Saving over 6 hours just by not being killed prematurely.
Exactly. Simply because jobs weren't being randomly terminated by deployments anymore. Overall, across the platform, dataset replication speed improved by 10–30% because the source data was reliably available sooner, and the P95 end-to-end registration time for new datasets generated by LRJs reduced by 30%.
Faster time to value for the data.
Right. It was a huge success in making Kubernetes a viable, robust platform for these critical, long-duration tasks, overcoming that initial scary roadblock.
That's truly impressive. A great example of adapting architecture to a new environment. Beyond the orchestration and job lifecycle, what about the underlying network and streaming interactions? You hinted at issues earlier. What kind of persistent flakiness was Moana, our Spark job framework, experiencing when writing data to M3? More problem statements there.
Oh, yes. Network flakiness is the bane of distributed systems. Moana Spark jobs, which write Parquet files to M3 via our custom M3 Hadoop's client.
The Hadoop file system client for M3.
Right. They were frequently failing with really cryptic errors like read end dead or unexpected end of file from server during writes.
Read end dead during a write. That's confusing.
Very confusing. Took a lot of digging. The root cause turned out to be a really problematic write pattern that Spark itself exhibited in certain situations. It would write just 4 bytes. Literally 4 bytes to start the connection.
4 bytes.
4 bytes. Then it would pause, sometimes for a surprisingly long 15 to 20 minutes, while it did more processing or gathered more data before resuming the actual bulk write of the Parquet file.
A 15-minute pause after just 4 bytes. Why would it do that?
Internal buffering, complex query plans. Reasons varied, but it happened. And this hidden behavior caused a lot of headaches with our infrastructure.
I bet. A 15–20-minute pause after just 4 bytes. That sounds like a recipe for network timeouts and connection issues from anything in the middle.
Exactly. It was an idle timeout trap. Our M3 load balancer specifically, an F5 layer 4 load balancer we used in production.
Layer 4, so just looking at TCP connections, not HTTP requests.
Right. It operates at the transport layer, focusing on network addresses and ports, doesn't understand the application protocol above it. It would interpret that long pause after only 4 bytes as an idle connection and just prematurely terminate both ends of the TCP connection.
Killing the connection because it looked dead.
Yep. On the client side, Spark writing into M3 Hadoops. This would eventually lead to error rating request body to server messages when it finally tried to send more data. And on the M3 server side, it would manifest as an early EOF error because the client connection disappeared unexpectedly.
Nasty. And hard to debug if the LB is in the middle.
Very hard. We actually saw many failures occurring precisely at the 10/17th byte mark during the write, which turned out to be tied to interactions between our chunked transfer encoding, Spark's buffering, and the load balancer's specific idle timeout behavior. Because the load balancer was low-level and didn't provide application-level logs, it was really difficult to debug without deep network packet capture and analysis.
So the load balancer, just doing its job based on timeouts, was being too aggressive and prematurely cutting off legitimate, albeit slow-starting, Spark rates. Were there other flaky issues with M3 operations, perhaps around more complex file or directory management, beyond simple writes?
Yes. We definitely encountered other issues related to how clients interacted with M3. We also encountered a missing dataset issue.
Missing dataset.
Yeah. It was a rare but critical race condition during complex directory operations. Specifically, renameter and delete error happening close together, maybe orchestrated by a cleanup process. This could lead to situations where a dataset, despite being successfully moved or renamed, was then incorrectly marked for soft deletion by another process before the rename operation was fully committed and visible everywhere.
So it got deleted right after being renamed.
Essentially, yes. Leading to it being missing when a subsequent job looked for it in the new location, or worse, being accidentally garbage collected when it shouldn't have been. Then there was another fun one. 0-byte file writes.
0-byte files, empty files.
Empty files showing up when they shouldn't have been empty. When connections were reset by the M3 load balancer right at the end of a write, M3 could sometimes incorrectly record a 0-byte file as successfully uploaded, even if the actual content being sent was non-zero.
So the server thought it got an empty file.
Right. The client, meanwhile, would often not receive a final success response because the connection was dead, leading to data inconsistencies. A file exists, but it's empty. And the client might not even know for sure if the operation succeeded. Phantom empty files.
It sounds like M3, being an object store, was perhaps being treated too much like a traditional file system with strong atomic directory operations by the clients, but maybe its underlying atomicity guarantees were designed differently, leading to these mismatches and race conditions.
You've hit on a crucial point there. That mismatch in expectations was a source of many of these inconsistencies and tricky errors. Clients, especially coming from an HDFS background via M3 Hadoop BEFs, often treated M3 like a standard PSIX-like file system with atomic directory operations. They assumed that an operation like renaming or deleting a directory would either fully succeed or completely fail, leaving no weird partial state.
The all or nothing guarantee.
It's exactly. However, M3, much like its inspiration AWS S3, really only guaranteed atomicity for per-file operations, like put-t, get, delete on a single object. It did not provide strong guarantees for complex multi-file directory operations, like an atomic renumerator that might involve manipulating thousands of objects underneath.
So the abstraction was leaky.
Very leaky. This mismatch in expectations between the client, which behaved like an HDFS client expecting atomic directory operations, and the underlying object store's actual guarantees, was a fundamental architectural problem that caused many of these flaky issues, race conditions, and data consistency headaches.
Okay, so a whole host of tricky issues stemming from network behavior, load balancer timeouts, and mismatched expectations about atomicity guarantees. How did the team go about building client-side resilience to fix things like the read-end dead errors and improve the reliability of these complex file operations for the M3 client? You couldn't easily change Spark or the load balancer, so the client had to get smarter.
Pretty much. We had to make the client more robust to the environment it lived in. For the read and dead issue caused by Spark's pause, the primary fix involved buffering the first chunk of writes, say, the first 4 KB within the M3 Hadoop pass client itself, before making the initial network call to M3.
Buffering before sending.
Right. This effectively primed the connection with some initial data quickly, satisfying the load balancer and preventing it from terminating the connection during Spark's subsequent, potentially long idle period. For even longer stalls after that initial chunk, temporarily buffering the entire file client side was the less efficient fallback, but sometimes necessary.
Clever. Working around the LB behavior, what about the rename race conditions?
To address the missing dataset issue resulting from renumerator delete here race conditions, more robust logic was added to the M3 Hadoop client's rename implementation. It essentially stopped assuming the server's first response was the final truth. It ensured that a rename operation, writing AB, was only considered fully successful if both the server and the client agreed on the outcome. This often involved adding client-side validation steps, like comparing the directory listings or checksums of the source A and destination B after the rename, and implementing retry mechanisms if inconsistencies were detected, forcing a consensus.
That's smart, effectively changing the client's behavior to be more defensive, to outsmart the load balancer timings and reconcile state across operations. What about the 0-byte file problem and just generally handling stalled streaming writes more robustly?
For the 0-byte files, the client was made much smarter with enhanced retry logic. And critically, we added a validation step at the file close, staged within M3 Hadoop. Before declaring the file successfully closed, it would explicitly check that the bytes transferred reported by the operation matched the bytes written by the application.
Verify the size on close.
Exactly. If they didn't match, or if an error occurred suggesting a reset, it would retry the write. We also introduced a small delay before these retries to give the server time to potentially clean up any previous, potentially erroneous 0-byte file state from the aborted attempt.
Okay. And for general streaming rate stalls?
To address general stalled streaming writes more broadly, the adoption of multi-part writes, which we'd already implemented for large file reliability, was suggested as the best long-term pattern, even for files that weren't necessarily huge, but might be written slowly or intermittently.
Using multi-parts even for smaller, slower writes.
Yes, writing files in chunks from the client and having the server assemble them. This approach significantly enhances client-side PUT reliability in the face of network failures or long pauses, and naturally helps bypass M3 load balancer timeouts because you're sending smaller chunks more frequently, keeping the connection active rather than one long, slow stream.
So it's all about building resilience directly into the client, making it more intelligent and defensive about how it interacts with the less predictable underlying object store and network infrastructure.
That was the key takeaway. Assume failure, build resilience in the client.
And what about proactive recovery? If things still went wrong, say a node died, causing data sets to become under-replicated, how did Maestro handle that automatically, ensuring data was always available?
That's where Maestro's dataset auto-healer component came into play. This was a background process designed specifically for this. It proactively scanned the cluster's metadata, identified datasets that were under-replicated, meaning they existed on fewer hosts than the desired replication factor dictated.
Finding the endangered data sets.
Exactly. And then it automatically initiated peer copies to bring those datasets back up to the required redundancy level, ensuring data availability and durability across the cluster.
Auto-healing. Nice.
This auto-healing mechanism was continually refined over time and eventually applied to all queries and dataset accesses, not just specific types, making it a ubiquitous safety net for data availability. We tracked metrics closely, like the number of repair attempts initiated, the number of successful repairs, and deduplicated repairs across various superpods to ensure its effectiveness and guide continuous improvement. It was all about constantly improving data resilience in the face of inevitable hardware and network failures. Hashtag tag outro.
And that, my friends, brings us towards the end of an absolutely incredible deep dive into Maestro Superpod.
It's been great charting that journey.
We've journeyed through its remarkable evolution, haven't we? From its humble, kind of rigid beginnings tied to single hosts facing those insurmountable scalability walls.
Yeah, feels like a long time ago now.
To becoming this distributed powerhouse, a system that now expertly orchestrates petabytes of data, manages millions of daily jobs, and navigates these incredibly complex encryption and security challenges with grace and ingenuity, it seems.
A lot of hard work from many teams went into that.
We've seen how a relentless focus on identifying the core problems, really understanding the problem statement first, whether it was architectural bottlenecks, that delicate dance between security and performance, or the real intricacies of distributed data placement and robust fault recovery. How that focus led to groundbreaking, impactful solutions, often forged, as you described, through intense architectural debates, navigating stakeholder differences, and sometimes learning from unexpected setbacks like that few C performance regression.
Absolutely. Those failures are often the best teachers.
Right.
And understanding the why behind a problem, getting all stakeholders to agree on what the problem really is, that's often half the battle.
What's truly fascinating here, listening to this, is that this isn't just a collection of cool technical fixes. It feels more like a profound story about the deliberate multi-year effort to build what you called a reliable, available, secure, and scalable foundation platform.
That was the goal, the mantra. RAS.
And this platform is the very engine powering critical analytics for Fortune 500 enterprises. Ultimately, it's about ensuring customer satisfaction through its ability to operate at extreme scale and under these diverse, demanding conditions. The journey of Maestro Superpod really highlights how deeply understanding the true problem statement, even when it involves navigating those complex and sometimes conflicting stakeholder priorities, is the first and most critical step towards a successful, lasting solution.
Couldn't agree more. Clarity on the problem is paramount.
Absolutely. The lessons from Maestro Superpod, I think, resonate far beyond the specifics of this particular system. It really highlights how the most profound innovations often emerge not just from clever coding or implementing the latest buzzword technology,
No silver bullets.
but from a deep, almost forensic understanding of why things break at scale. And having the courage to rethink fundamental assumptions, even if it means admitting initial approaches or widely used components were flawed in your context. It's about that continuous cycle of learning, measuring, adapting, and perfecting, especially when facing the intense pressures of real-world scale and critical customer demands.
Well said. And that raises an important, maybe provocative thought for all of us working in technology today, especially in distributed systems. As these systems continue to grow exponentially in complexity and scale, what unseen assumptions might we be making right now? What implicit beliefs about our tools, our architectures, our operational models might be limiting the next generation of scalable systems?
What are today's single host assumptions, or fuse is the only way assumptions?
Exactly. And perhaps more critically, how will we cultivate the curiosity, the systematic approach, the measurement, the profiling, and the humility required to uncover these hidden assumptions before they become the next petabyte scale crisis or the next 85% CPU bottleneck?
A question of continuous vigilance.
It's a challenge that never truly ends in this field. It demands constant vigilance, a healthy dose of skepticism, and a fundamental willingness to question everything, even the things we think we know best.